Yeah, okay. So I'm Robert. Robert Virding. I now work for Erlang Solutions. We do training and consulting in and around Erlang. We're also developing a few products with that as well too. So if you want Erlang consulting or stuff, email me. I'll give you my mail address later. Okay, keeping history short and wandering straight into the presentation. Okay, so what I was thinking for the presentation was to keep it at a fairly general level. And if you have more specific questions, please ask them, and we can go down and look at stuff for them. Relative. See why we're doing. Result is why something 25 years old is still very usable, and details of the internal details of the machine to show why things work. And as Rob knows, me when you've had enough, right? Because I'll keep on going. Yeah, we're going to answer. Me, I was originally a theoretical physicist. Okay, this is yes. That was a long time ago. Okay, physics has changed since then. But I was postgraduate, and the physics department got their own computer, so I had free access to that, and I thought that was fun. And a while later, the physics department and I decided I should go do something else because I wasn't doing physics anymore. Right? I was just programming. I started working for Ericsson, the telecoms company. Originally in a small group managing VAX VMS computers in the Stockholm area. Yeah, I live in Stockholm. Okay, that's where I come from. That left me time to do other things. Amongst other things, I was porting France Lisp from Berkeley Unix to VMS. And no, I have absolutely no reason why no one actually wanted that. It was very much fun doing it. Especially if you wanted to do compiled Lisp. Interpret Lisp was easy, the compile was more difficult. If anyone wants to hear details, contact me later. Yeah, so there was a relatively newly formed computer science lab in Ericsson, and they sort of heard about me and I heard about them, and that was sort of the place. We decided that was the best place for me to work. So we started working there, and our group was interested in actually introducing new technology into Ericsson we thought would be useful, and also trying to spread it, which quite a few labs weren't doing. Just within Ericsson, other labs as well too. We're actively trying to spread out our ideas. So that gave us the chance to look at a lot of new languages, or different languages rather than new. So we did quite a lot of work with Lisp. I did some of that, both implementing Lisp and working with Lisp. We migrated over to logic languages. This was the 80s when logic languages were very big, especially in Europe. So looking at Prolog and a number of concurrent logic languages, which I think are fantastic. That got us into looking at, we're trying to sort that. Parallelism. And there are a lot of concurrency, a lot of definitions of parallelism. Some of them equate, some don't. Equate them. But I think is your solution to a problem provides. Okay, this is a sort of a level for it. And current application with lots of concurrency in the application, running on a parallel system or running on a non-parallel system. I still have the running on a parallel machine, which is a total waste of time, but I can do that. So there are two good things. About doing Erlang was the concurrency. The problem we were looking at was very concurrent, so that's what we were interested in. We didn't have access in those days. We're talking late 80s now to parallelism, so we didn't have access to that. So yeah, so that's a little bit of history. I can also say I have done very little Java programming and very little Python programming and very little JavaScript programming. So I'm sort of handicapped in the other direction. And I don't believe in objects. Okay. Yeah. Not even Joe's objects. I don't know if you've seen that. Joe Armstrong, he was one of the, actually the first person started working, developing Erlang. He says Erlang is the most object-oriented language in the world. And he's going back to something Alan Kay has said, where Alan Kay said for him the most important parts of object orientation were messaging, true messaging and isolation. This thing with classes and hierarchies and so on, that wasn't for him. That wasn't important. And from that point of view, Joe says Erlang is the most object-oriented language in the world. Most of the rest of the world don't agree with it. But, yes. Anyway, yeah. So it's a bit of history. So what we were trying to do was this. So Ericsson they still have a switch called the AXE. This was developed in the 70s. It was an extremely good switch, an extremely successful product, made Ericsson a ton of money, and is actually still being used in their systems. But even if successful, it was costly and difficult to maintain. So we were looking at the problem that how could we... that's a real picture, by the way. Okay, this is old stuff when we're still having wires for, but a telephone exchange could look like this, and that was one cable per telephone going up. So if something went wrong, trying to find out which cable was basically impossible. But yeah, so we're looking at how could we program telecoms type applications in a better way. Now we ignored things like stability and stuff. We were looking at, and by Joe Armstrong, he did get one running, that's great. Then of course you want to have multiple cores running, and you have it running the concurrency problem. We just getting more and more and more. So yeah, we were 3 people initially doing the basic Erlang system. Was Joe Armstrong, was so what was the problem? So the basic problem domain, this comes from our boss in the lab, Jan Decker. He wrote a thesis on this, describing these 12 points, which were describing the problem we're trying to solve. Okay. So you have actions performed at certain times. You need distribution. You need fault tolerance, and if you want to make a fault tolerant system, you need at least 2 computers, which means you have to have some form of distribution handling between these machines. Controls hardware, large systems, complex functionality, continuous operations in many years. You're not allowed to take the system down to do stuff. If the system crashes, that costs you a lot of money. Okay. Everything should be performed while the system is running without stopping. You need fault tolerance. Things will go wrong, the system should not crash. You need to be able to handle a large number of concurrent activities. So I don't know what it is today, but in those days, a typical large switch might have a few 100,000 connections coming in, telephones coming in. You might be running tens of thousands of calls on the thing at one time, plus it's doing a lot of other stuff. So this is interesting, and some of these are very difficult. Well, uncommon at that time, like handling large number of concurrent activities. This C10K stuff, we were thinking C100K, okay, 20 years ago. So that's the scale we were thinking of. You have things like fault tolerance. Yes, errors are going to occur. How do you stop the system from crashing? The system's just not allowed to crash. This one hides a lot of interesting detail. You have timing constraints, which means, for example, nothing is allowed to block the system. The whole system has to be non-blocking, for example. Things can't take too long time. All the things that are becoming interesting today, these are just parts of that basic problem we were looking at. This private business, Ericsson Business Exchange, we had a lab with 4 telephones connected to it. So they do actions, get telephone, so we could make calls through us. We were testing, programming these type of applications in any language system we could find. I think we must have done about 30 or 40 Unix machines. Some simple, some were quite complete. So, for example, we did a big one in Ada. One of our guys did a big one in Ada, and that worked quite well, but we found the Ada rendezvous just did not fit the problem at all. So I had to do a lot of work to get around the rendezvous problem. The whole thing's basically asynchronous, whole thing like this. And what I was doing there was, we were going to a trade show, and we were going to demo Erlang, and coming along with us this small switch here, which is one little light on saying it turned the power on, is very uninteresting to most people. So we thought, how are we going to lure people to come and listen to us? We did a train set instead. So we had a train set. I don't know if I've got any films of it actually for it, but which had an ATC system written in Erlang controlling the trains. So we had a board running up there with 2 trains on, and we could run them on. They wouldn't collide with each other. We could program in schedules for them, how they were going to run, and this type of things for them. I suppose today you'd say we had a DSL for describing these things. It was quite a lot of fun. It worked too. It ran for a week. We also used it for courses. There's just a little bit of philosophy, a little bit of the history behind us getting into these things. So we'd done work a lot in the 80s looking at various things for doing these systems that finally end up in developing Erlang. Yeah, some philosophy for this thing. And some reflections here which I think are very important for what happened is that we were not originally we were not trying to implement a new language at all. Specifically, we're not trying to implement a functional language. I don't know if this is sort of swearing in church here, but or it's just proving the power of functional programming. Take it whichever way you want. We were not trying to implement a functional language. We were not trying to implement the actor model. Yes, Erlang more or less sort of follows the actor model, but we were not trying to implement the actor model. We didn't even know about the actor model. Okay. What happened with it, we were working with Prolog, and we were modifying our Prolog system to get to fit into more what we felt our requirements were. And a couple of years, the model. You go. We had a problem with these characteristics of the problem goal. And I think very problem. That means any new feature we could come up with, we could test and say, did it help us solve the problem, yes or no? If it was no, we could just get rid of it and try again. And this was not just in the language implementation, but how you build structures on top of the language for building these systems. How do you do it? You get feedback for it. And we were very lucky. We had from early on, we had another group inside Ericsson, who were doing an architecture study, and they wanted a language to prototype their architectures in. And they were much more knowledgeable about the telecom side than we are, or we were. At least Joe and I. Joe and I knew very little telecoms, Mike knew quite a lot of telecoms. But we had this very good feedback. So they could test our language to make their systems. They could look at our new ideas and say, yes, this helped, or yes, or no, we couldn't use it. So we had a very clear focus on what we were trying to solve. So what went into the language, what went into the system design was to solve this problem. And what this resulted in was some basic principles we felt were fundamental to the problem. So this lightweight massive concurrency, that was such a fundamental part of the problem that if you couldn't solve this, any solution would be uninteresting, no matter how good it was. So we decided, okay, you put primitives for doing the concurrency and the communication, bake those into the language. They're too important to put in a library above it. From our point of view, they're almost as important as doing a function call. That gets back to the problem of fault tolerance. So we had processes in the system. Processes had to be isolated. If something went wrong with a process, the process would crash and then you couldn't ruin things for other processes. Which means, for example, you could not share data between processes. And these type of things. So you had process isolation. Fault tolerance, also a fundamental part of the problem. Interesting. So, and again, we're thing there. Principles for building, how do you build fault tolerant systems and what basic tools. So, constraints in the telecom world, you have these timing constraints. Real-time people don't call this real-time. Okay, we say hard real-time. So for them, if you miss the time, you had to solve these problems. So this was at the domain and how you would solve the problem domain. The AXE system did it. Other had exactly the same problem domain, but they did it a different way. And what I find quite funny is the way they did it's pretty much the same as what Node.js does today. Okay, but that was about 40 years ago. Sorry. Yeah. Okay, some secondary principles we had. We wanted a high-level language to get real benefits of it. Okay, in those days, most languages were pretty low level from today's point of view, but we wanted a high-level language. We wanted a simple language. There are a couple of reasons for this. One, to make it easy to implement. The more complex your system is, the more difficult it is to implement it. The harder it is to work with it and change it as well. And to make it easier for people to learn. So our idea was that if you could get a small number of correct basic principles, that was the goal. Then you could build anything else you want on top of that. Can we avoid putting complex things in at the low level? Can we put just simple things at the low level? Then you build your complexities above it. So, for example, we have asynchronous communication. That is the only communication means you have. If you want synchronous communication, you build that on top of the asynchronous stuff. That also means that whatever type of specifics you want for your synchronous communication, you can explicitly code them yourself. You don't get what someone else thinks is what your synchronous communication should look like. The same thing with the error handling mechanisms and so on. And I think we succeeded. That's something I'm a bit proud of. If you look at the concurrency primitives and the error handling primitives in Erlang, they are extremely simple. You have processes with process isolation, you have asynchronous, you have a waiting receive. That is communicate. That's concurrency. We managed to get a number of very fundamental principles at the top of it. Wide solution. We try solutions and we use. Okay. Get that's how we can't use it, and we just understood the problem. So we were in the solution. So what is it? It's a simple sequential functional language. It's a simple functional language. Okay. It has a slightly different syntax, but then again, all functional languages have a different syntax. No functional language has a syntax that looks something like Java or C or whatever like that. Not even F#, right, which comes from a big provider, has a syntax that looks like the other sharp languages in the system. It's just a fact. It's safe, which today is quite common, in the sense we don't have explicit pointers or anything like this in the system. We don't have explicit memory management or anything like this. This is quite common today, but in those days it wasn't. This was before Java. We were before Java, and we had garbage collection, we had a virtual machine, and all these type of things, which in those days you could just not do in a production system. Today you can, but those you couldn't. It's dynamically typed. There is no static type system for it. Okay. So we don't go the Haskell way for doing this. There are a number of reasons we did this. I can talk more about them later if you want, but there are a number of reasons we did this. Someone has said it because we couldn't write a type system. Well, we learned to write compilers and we learned to implement these languages. If we want to do a type system, we could have done one of those as well too. Just read the book, right? It's not. While you read the book on how you implement languages, you go look at a few implementations and you do one. Right? You want to do garbage collection, there are a ton of papers describing how to do garbage collection. Pick one and implement it and it works. The interesting thing about this is, if you look at these papers and you follow the references back, you end up in the 60s somewhere for all this stuff. Sorry. Anyway, yeah. So yes, the reason was not that we couldn't do it. We hadn't done one. Define data. The one of elements, and you have lists. That's it. You build everything on top of that, and there are a number of types as well too. Again, with Erlang records, they're syntactic sugar for tuples. We don't. We use, and you have to know about it. Yes. No. New maps are new data type. So that's the latest data type we have. It's a map. It's a built-in key value store, hash table, whatever you want to call it. They're a new data type. You can build things. If you want other things, you build them on top of that. Some other things we have, these are typical things for functional languages. So there's nothing strange here. We have immutable data. All data is immutable. You cannot fix mutable data. There's no way of getting around that system. That's baked in at the very low level for immutable data. That's one of the things I don't like about Scala, to be honest. The fact that you can mix functional and object-oriented. And in worst case, you can say you're programming functional, but you're actually just programming normal, like Java with a different syntax. Okay, I'm being nasty here. But yeah, so we have immutable data. And you might be able to get around it in something called an if, but there's no guarantee the system will work afterwards, right? You might actually crash the system doing it. We have immutable variables. This, again, is common in functional languages, although we don't have scoping, so it looks a bit strange. It looks much more like what you have in Prolog, Prolog handling of variables there. Erlang was originally developed on top of Prolog, and then we wandered off from there. And there is nothing left in the Erlang semantics that come from Prolog. There are a few syntactic constructions that are left from there. How do you mean? Okay, I'm saying immutable data. If you make a data structure, you create a data structure, I cannot go in and change that. I cannot go in and change a field. If I have a list, I cannot go in and change an element in the list without doing some copying. It's just, this is sort of hardwired into the system. Yeah. Okay. So yeah, that's one of the things people complain about. I don't find it a problem. I find it easy to. That's for everything. I don't know if you haven't worked with pattern matching is fantastic. Operators or anything like this, building structures, you write down the structure you want and the system will build it. When you want to pull something apart, you don't tell the system how to pull it apart. You say, what do I want my structure to look like? And the system will build code that pulls it apart, tests and pulls it apart for you. So it's a really powerful tool. If you haven't used it, it's a rethink. You're saying what rather than how. Okay, which is very nice, very functional, but if you're not used to it, it can be quite difficult. So ask the guys in the course for that. It's a step around. Yeah, and there are no looping constructs. This is functional. There are no looping constructs. You could write one, but it'd be pretty useless anyway because of the immutable variables and things like this for it. So yes, we use recursion for everything. Again, this is standard functional fare. But if you're coming, say, from object-oriented language or C or something like this, then you've been explicitly told, don't use recursion because recursion's bad. Right? Here we say, yes, use recursion because recursion's fantastic. So yes. Yeah. I don't have many language examples. I can give you more later if you want them. Well, I have one which I think is really fantastic. Sorry. For pattern matching everything. So we have a binary data type. And at one level is completely uninteresting. It's an array of bytes. Now, how much fun is an array of bytes? What we do have, however, is a declarative way of accessing that data. So we can say that this thing, which is an array of bytes, consists of a sequence of segments of various data types of various sizes in it. And we can use that both to build a structure like this and to pull one apart. So this binary here, this binary representation, is an IP version 4 data packet in one go. So if you look at it here, you see it consists of, well, you've got a 4-bit IP version. Length. ID, 3-bit flat, the whole thing. I've got a complete description of an IP packet in one go. I can to build the IP packet in one go. Or if I want to pull it apart, I can use that as a pattern and pull the IP packet apart. Yes, packets, but you're working with a lot of other protocols which have data in packets, and you can use the thing to pull them apart. And the handling of the packets was completely trivial. You just wrote down the pattern for each packet and pulled it apart, and you use the same thing when you build new ones for it. Yes?
Yeah, I had to reverse engineer the Oracle SQL protocol when I was here, and it was so simple.
Yeah.
Like, you're just declaring, this is what I expect at this bucket range, and I pull that out and I can use it however I want. It's awesome.
Yeah. Yeah.
On the other hand, I write network drivers and protocol handlers and stuff at this level in C, and I can vouch for the fact that there's about 20, 30, 50 times as much code.
Yeah.
And likely to get some of it wrong.
Yes. Done that. Been there. Right. Yes. Yeah, I've fiddled with bits in C as well too. So yes. Yeah. So getting back, I haven't done much Java or Python or JavaScript programming. I've done quite a lot of C programming. That's what you use to implement languages. You use C to implement languages. And I've done a number of language implementations. I've even written Fortran code, Pascal actually. That's how long time ago it was, and BASIC as well too. And well, a number of Lisps and functional languages. Yeah.
Also, that in Cowboy, which is a web front end for Erlang, it gives you a pretty decent API for destructuring what's in HTTP headers, request headers.
Yeah.
It's a nice way to just destructure stuff that you would expect on an API perspective as well.
It's yeah. This is just sort of taken to the limit of using data. I don't know if any other language has this. I think someone said something that Haskell had something along these lines, but I don't know. Okay. Yeah. It's just something so fantastic. Once you get used to it, you can do it. It makes things very easy for it. Yeah. So that's why I've included that for it. This made things easier. Okay, some more points here. Okay. We program the case that works, and if something goes wrong, we crash it. Okay. That's the base. We generate an error. This because you start doing error handling in code, it grows, and you have to do it everywhere because you can get errors everywhere. Errors anyway, so we might as well just let things crash. Else clean up after. So I'll show in a moment how you do that. So we don't very seldom program defensively. You program for the correct case, someone else will fix up for you. It's like pouring water on the floor, then just leaving. Right? Someone will clean up after you. Right? So yeah, that's the sequential language. I can have more examples for it. I think I have a few more. Yeah, that concurrency. So this is a quote by Mike Williams, who was the third guy in the initial group. So we were 3 people who did most of the basic Erlang. Then it grew afterwards with other people came in and added some other new features, binaries, for example. And his thing was there that if you're going to use programming language, concurrent things for operating systems, there are 3 properties you need. There are 3 things you have to keep short. That's creating processes, context switching between processes, and communicating, sending messages between processes. If you want a fast concurrent system, you have to get these working quickly. Okay, otherwise it just doesn't work. And if you've got a highly concurrent system, this is just basic to it, fundamental to it. So these type of things we're looking at. So yes, we implemented processes in Erlang. We did processes, but we're not talking about operating system processes here. These are things, operating system processes, just things that are way too heavy for the type of things we were doing. Yeah, we can have millions of processes running on a machine. Erlang processes here. And there are actually production systems that do that. WhatsApp is the best example of it. So they came out 2 years ago and said they had a system running one machine which could handle 2 million concurrent TCP connections on one machine. And running through an Erlang system. And they probably had at least one Erlang process per concurrent connection. And one of them told me privately that at one time they were peaking at 3 million. So a lot of process system. Yet that means that processes have to be light. They cannot be big. We're not talking about operating. It's very operating things, but and all processes. So sometimes people processes, but they're just processes started by the system. There's nothing about it. So it's a very egalitarian system. have a lot of processes. So there aren't many cases you're done with it, it goes away, like in the cowboy case. You open up a connection, you create a process to handle that connection. When your connection goes down, you remove the process. That's just the way of doing it. And we use processes for everything, not just for concurrency. So we're using processes to model concurrency, yes, but we're also using it to manage state, because there is no global data in the system. Everything's encapsulated in these processes. So if you have state you want to share, you wrap that state inside a process, and other processes then communicate with that to access that data. And okay, some of you might have heard of ETS tables, but they're actually very process-like when you start looking at them. They're not shared data. There is no shared data in the system at all. And processes are isolated in the sense that from one process I cannot directly affect the data in another process. So I cannot go write in some other process's memory area or anything like this. I can send a message to it, but I can't write it. And this you need for the error handling. A process can crash. If a process crashes, it must not ruin anything for any other process. So this is why we're talking about processes, not threads. Again, this is very much like an operating system process. An operating system process crashes, you might lose a service, but you're not going to ruin it for other processes. You're not going to go in your write memories and ruin things like this for it. And processes will crash. There's no shared state. You'll never have the problem that someone's updating shared state and dies in the middle and you get something which is inconsistent. That you just don't get that problem. So how do we communicate? Everything's done through message passing. So if I want to tell a process something, I send it a message. If I want to pass a data, I send it a message. If I want to ask it to do something, I send it a message and it will send a reply back telling me when it's done. So for all communication, we use message passing. And we use asynchronous message passing for everything. There is just asynchronous message passing in the system. PID, I can send a message to the process. And we have a select mechanism. So send puts queue, sending a message to it puts it on the message queue. That's all the send does. And when the process get hot message, it can do a response. Which I can say what this. So and if it's not there, I'll wait for it until it comes. The message will remain on the queue. Yeah.
Okay, processes are running on the same machine.
Yeah.
Do you actually copy the data, or
Yes.
do you just pass it?
We copy it.
It's immutable, right?
Yeah. I've got some more things to say about that a bit later on the details. Some details in the implementation, how we do this type of stuff. It's all just that problem. Yeah, we do copy it. Yes.
How big are the message queues?
From 0 up until we run out of memory. Literally. Sorry. Yeah. There is no limit. There is no built-in way of limiting the size of a message queue.
So you can send a process 1 million messages.
You can send 1 million messages, and you can fill up the system and crash it doing that. Yes. Yes. There are a number of standard ways of crashing Erlang, and that's one of them. Okay. Yep.
I saw a pull request or an issue open on OTP that talks about bounded queues and they're
Yeah.
having a discussion on doing it. Do you know the progress of that?
No, I think I saw that. Was that the one who was doing priority sends as well too? No. Okay, there's one doing priority send. Yeah. I don't know. It's come up occasionally. I don't know what's going to happen. The problem with doing bounded queues, talk about this. Yes, why not have some form of doing bounded queues? The problem with that is, what happens if the sending process is sending to a process with a bounded queue and there's no space left? What's it going to do? Then I'm not asynchronous anymore. Then I'm suddenly synchronous in this because I'm getting back and saying I can't send to it or get an error or something like this. I could do an asynchronous version, I send to it, but then I'll get a message back saying, no, you couldn't write, the message queue was full. So you get all these problems asynchronously about. And now Everything except for one thing is asynchronous, and if you lose that, you're going to cause problems elsewhere. So yes, consistency wins in the long run. So yeah, the message queue can be at any length, and there's no way of doing that. There are ways of asking a process how long your message queue is, so you could do servers do that. Message queue, then I'm doing synchronous sends to it, which will block the system. Yes. They'll be put in the queue in order. Later do that. When I do a receive, I can say, yes, I want to look at a message. Has that structure. And the other ones I'll just ignore for the time being. They were in the mailbox, but I'll just ignore them for the time being. So for example, if I'm writing a server, so people are going to send me requests. I'll have a top loop getting requests, and I'll process the requests. Now, of course, while I'm processing a request, someone else might send me another request, but I don't want to see that until I'm done. But at the same time, I might want to be communicating with other processes while I'm processing and doing the request. In that case, I just want to handle messages I get from the other process and ignore the request for the time being until I get back to the top level, then I'll take the next request. And that's what the selective receive allows me to do. I can say, yeah, now I want this message. I'll ignore everything else for the time being. And that, if you think about it, that means you avoid a combinatorial explosion of states and messages. Otherwise, worst case, I'd have to be able to handle every message that could conceivably come to me at every state. And that blows up very quickly. So yeah. So yes, that's what the selective receive does. And on top of this is the basic mechanism. That's it. Literally, that's it. Asynchronous message passing, selective receive, and that's cross-spawning processes. That's concurrency. So it's those 3 or 4, depending how you want to count the things. That's the basis of it. That's what I was saying. We managed to keep it very small. And on top of that, then you build what you want. If you want synchronous communication, you send the request, and the server sends back a reply, and I sit and wait for the reply. I do that with 2 messages. That also allows me for me to build my synchronous communication the way I want it to be built. If I want to put timeouts in, I can put timeouts in. If I want to put a more complex error handling and detect if the process the other end crashes, I put a more complex error handling in with detects that the process crashes. If I don't want these things, I just ignore it. Maybe I just be a send and pray. I'll do that. It allows me to do whatever I want. Communicating with the outside world from Erlang. One is ports. It's to something on the outside. I can send messages to it. If I send a message on the port, it will arrive at the back from the port. So the outside world looks like async. And they obey. I haven't said it here, but I mean, it runs concurrently, independently. I communicate using messages, and we'll see in a moment it obeys error handling for it, and that's what a port does. So if I want to talk to the outside world, I'll open a port to it, and I'll communicate with the outside world sending messages. If I'm using links for the error handling mechanism, something goes wrong, then the port will be closed. I'll find out about it, or if I crash, then the port will automatically be closed, and all these type of things for it. So it behaves like a process. Yeah. So yes, At one time, we were actually discussing whether to have a separate port type or just make them look like normal processors. We went for going with ports. So the other way of communicating with the outside world are through NIFs, natively implemented functions. And that's a way of calling a C function from inside Erlang to make it look like an Erlang function. I define something as a NIF, yes? Natively implemented functions. They came a few versions ago, now they're standard. So I define something that looks like an Erlang function, I call it, it's actually C at the other end, and there's a big library which allows me to access Erlang data which I can do things with. I can do anything in that. That's another way of doing it. Which one you use depends on what you want to do, stuff like this for it. For example, one problem with NIFs is that if you make a bug in your C code, say a segment violation, you take down the whole Erlang system. You're running without safety nets. If you make an error in your Erlang process, say divide by 0, you crash the Erlang process and everything else happily keeps going on. So if you're in NIFs, you have no safety nets. Yeah. So I have a simple example here. This is telecoms again. It's a toy example, but it actually worked. Okay. So it's not from a run. Talk to others using this. You could actually make telephones ring, and you could ring running through this system. Able to state machines in some nice way. So two functions. With dot number, and it is very in. So the A side making the call, and the B side one process, multiple processes for the call. Might seem overcomplicated, but it's actually much simpler. It simplifies the logic a lot. It simplifies the handling, and also makes it much easier to build on top of the system. So the A side, we've got the receiver up, and we can hear the ringtone in our receiver, and the B side, the phone's ringing. So what can happen? Well, on the A side, I can put the receiver down. I've given up, right? So I'm going into my state function here. I go into receive and say wait for a message, and if I get an on-hook message, that's what the system will send me when my caller puts the receiver down. What do? Well, I send cleared to the B side. That's telling it it's going down. So I'm sending a message to the B side saying cleared. Then I'm stopping the tone. I'm calling the teleOS here, which is our little operating system for stopping the tone. And I go to the idle state by calling the idle state function. So yeah, we do tail calls, tail call optimizations here. So that's the first thing that can happen. The A side puts the receiver down. Then we go look at the B side code here, and if it gets a cleared, that's being sent from the A side, telling us the A side has put the receiver down. So what do? We stop the ringing, and we go to idle state as well. So we have these two processes working. If one puts the receiver down, tells the other one now we're cleared. What else can happen on the A side? Well, we can get, okay, so what can happen on the B side? The B side person lifts the receiver, we get an off hook here. So what do? Well, we stop the ringtone again, of course, and we tell the A side we get an answer. And then we go to the speech state here, because now we're talking with each other. On the A side, they get an answered message, and what do? We stop the tone, we tell the switch to connect us together. This is telling the switch to connect our two phones together so we can talk with each other, and then we also go to the speech state. So that's how to handle both. What happens if you call someone and they're in the middle of a conversation? What do you hear? You're busy. What call tell you that they're busy, right? So while all this is going on, none of this is up. So while we've got the so we can't wait. We have to sit. Everything has to be programmed asynchronously. Yes.
So I know this is not real code, but in this sample, is there a particular
Generally, how which is handling the connections. So again, if you're in speech and one side goes down, if the B side goes down, then the B side will tell the other A side now I've hung up, and then it's the A side that takes the connection down. This is connection. So you have to decide who's going to do it. So both sides can't do it. If both sides try and do it, then the switch is going to complain and generate an error and stuff like this for it. These things were very sensitive. So it was quite fun doing this, because I mean you sit there, do it in software, and it'd be quite fun. Then you ran it on the actual hardware, and things would crash because you're doing things in the wrong order and stuff like this for it. The hardware expects a certain order for things. You had to follow that, and you could sometimes not find a logical reason for that. But that's just the way it worked. Right? And again, the convention here: I cannot set up the same connection twice. The hardware wouldn't accept that. I don't know why. So that's why the A side is doing it. So okay, so while we're sitting here, we can't block. None of this can block ever. So someone could actually send us a seize message. This is what we get when someone else is trying to call us. So if we're in the B side and get a seize, we have to answer this immediately. Say, no, rejected. You can't call us, we're busy. And then we go back to the ringing B side. The same thing here on the A side. If someone tries to call us, we have to answer immediately, no. And we go back to the ringing A side. And if we get anything else in here, we just ignore it. The system might be sending some message or something else going on. We just ignore those for the time being. Here, this just says, take anything, pulls it off. So the interesting thing here, one is that all this is done asynchronously. The whole system is asynchronous because nothing is allowed to block. Think if in your telephones, your mobiles, and you're trying to call other people, do things, and the system blocks, right? That, yeah. But you would be interesting. Yes, you had a question. Yeah. We also do tail call optimize. So that's the case of that. So with the last call, calling speech here, this last so this more or less optimized. A bit of with a jump. And that was something we wanted this type of programming in states. We basically changed state by just calling a state function. So we had this optimization in from the very beginning. It wouldn't work otherwise. If you don't have this optimization, then it suddenly becomes more complex. Expressing like this makes it very simple. So yeah, and again, this is standard functional language fare. Most functional languages have it. It's nothing exclusive to Erlang in any way. Closure doesn't, but they could have if they really wanted to. You can do tail call optimization on a JVM. You just have to do a bit of fiddling to do it. Right? I haven't done it, but there is an Erlang system running on the JVM called Erlang, which does it. So I know you can do it. You'll have to ask Richiki why he didn't do it. So yeah, this is typical type Erlang code for these type of things. Okay, so instead this is toy code, but actually made our phones ring on the system for it. And this is very typical of the style you're programming. In the style of these systems, they're all asynchronous for it. And that, if you haven't done asynchronous programming, that's a complete flip in your style. You never send off a request and wait for a reply. You send off saying something, well, tell me about it. And then so you get back later, you'll get back a message saying, yeah, it was 49. Okay, then you work out from this point of view for it. You just don't do synchronous stuff in it because it blocks. It happened, I think, about a year or two ago on the Erlang mailing list. The guy was talking about I've got my two servers working with each other, and when they call each other, they block. So how do I get around this problem? Right? And he had devised another solution. So he actually spawned an extra process to do the synchronous call so the original one wouldn't block. Yeah, it was smart, but the best answer. And it takes a bit of getting used to. First time's always. Okay. We're not allowing it to build up, but we're which message. Message on and checks as it. If it does, we take it that. Take the second message. So in this case, the first one that arrives will one that will happen. Yeah.
So does this example not implement the selective receive?
It's selective. Yeah. I'm saying here, if I get a message that looks like cleared, I'll do this. If I get one that looks like off hook, I'll do this. If I get one that looks like the tuple seize with someone trying to seize me, I'll do this. If I get something else, I'll just throw it away. So yes, I'm being very selective. I'm actually using pattern matching here to say which message I'm interested in and what do I want to do when I find one. Okay, in this case it's very simple, but yes. Yeah. It's linear. Every time you do a receive, you basically start at the beginning. There are a few special optimizations, but they're usually not ones you would do yourself. It's too easy to shoot yourself in the foot. You do that. Generally, it's not a problem if what you're doing. Yeah. Each of these state functions will have their own receive in. Yeah. Yeah. And what we're saying here, is maybe we both got an on hook and so we got an off hook and an on hook at the same time. So both of these are going to process at each side and do their bit and send messages to the other side. So here we're going to, if we get an on hook and an off hook, so the on hook will shut this down. The off hook will now send an answered, but we'll be in the idle state. When it gets an answered, it will just ignore it. Or maybe send back no, I can't remember. If we ignore it, there'll just be a timeout saying if we don't get an answer within a certain time, we'll just go up. So in all these things, you get lots of collisions for. You have to work around this. And that's what makes it so interesting to program these things. Ignoring it. Then you explicitly, might get other stuff, but so we had a premises here concerning error handling and fault. Your code error, the hardware will do straight. You will always get errors. I mean, yeah, it always occur. That's rule number one. So what are you going to do when errors occur? Well, the basic premise we have now is that the system must not go down. That's absolutely the worst thing that can happen, that you crash the whole system. It's just not allowed. If we're talking telecoms, if the whole switch crashes, that would cost Ericsson an awful lot of money if that happens. So that just must not happen. Someone asked Joe once, Joe Armstrong, what does never mean? And he said less than 4 minutes downtime per year. That's something like never. And I think it's 7 nines reliability. I think it's about 3 months. I think it's less than 3 minutes per year. Somewhere, I can't remember exactly, or was it 3 seconds? Well, anyway, we're down at that level of the thing for it. Well, and one product Ericsson produced on top of Erlang, a client was reporting they were getting 9 nines reliability, which is a sort of few milliseconds per year downtime for it. I have absolutely no idea. They weren't measuring one machine; they were measuring the whole system using that. So
So
yeah.
if you had a system with a raft of n processes, you just said, okay, I'm going to kill a random number of them, the rest are just going to keep going, then it doesn't matter what you do with it. I mean, just sort of being theoretically, the program that you created will keep on going.
Yes, but you have to build your system right to do that. Okay. So what we get with the error handling system, the system must not go down, yes, but parts of it may crash, but the rest of the system has to be able to recover from that. So, you had a question? Yeah, okay.
7 nines was 3.15 seconds.
Okay.
9 nines was 3.17.
Yeah. They were getting 9. This was a customer reporting 9 nines, right? Not us. Yeah, I'm very surprised actually. But yeah, but the system as a whole must be able to handle processes going down and crashing. So you don't take this down. And so what our have to build it yourself. There is support in the libraries for.
So if you kill all the,
If it was the right process, it could recover and start everything. If it was the wrong process, no, it wouldn't. You can't kill any. Always recover for it. The better you design your system, the smaller that kernel is, and the more errors it can be. The better it can handle errors in other parts of the system. It's not a silver bullet in that sense. You have to think about this when you're designing a system. So so the parts may crash and burn, but the system must never go down. That's the goal for it. And what that means is that the system has to be able to detect, contain, handle, and recover from errors. That's what the error handling mechanism provides you. It provides a set of tools for doing this. The libraries, they provide a set of tools built on top of the tools for doing these type of things for it, but you still have to use it and you have to architect your system for it. Okay. It's yeah. What have we got down there? Yeah, okay, so what about how does this mean about robust systems? Right? So what this means is, what we want, a robust system always has to be aware of errors, everywhere. But I want to program as much as possible so I can ignore errors. I don't want to do error handling everywhere. It's just a lot of error. So I want to be able to handle processes crashing among cooperating processes, and that has to interact well with the process communication, because that's how processes communicate with each other. That's the basis for it. And I was talking to one guy, and he said that before writing a system in Erlang, he had never thought so much about errors in his whole system as he'd done when he built the architecture in Erlang system for it. So what it means is, you can't ignore errors. You have to always think about errors when you're building a system. If this thing crashes, what do I do? Can I ignore it? Do I have to restart it? How do I clean up after it? And these type of things for it. If this thing goes down, if this service goes down, what do I do? If this call process goes down, well, calls we just let them crash anyway. You might lose an occasional call, but there's nothing to worry about, because the rest of the system thought as much about handling errors in the system as before designing an architecture for it. Because you're always thinking about the process. If you restart the with ignore errors in it. So, for example, the group was lines of code, and of those 15,000 lines they worked out that if you had somewhere between 600 and 900 lines correct, it could handle errors anywhere else in the whole system and could recover from them. Yes, you might lose calls, but the system as a whole would not go down. So yeah, that's the idea of the error kernel behind it. So yeah, we can do it, but it's not a silver bullet, and you have to structure it. Yes.
The interesting thing with other languages is you're actually still doing that, but the cool thing about Erlang is it makes it explicit rather than implicit, and it's very clear where errors go instead of like scattered throughout your whole code.
Yeah, it becomes very explicit for it. And it might feel very tedious when you're doing it, but it may as well work 5 years from now, 10 years from now. So how do we do it? We have a concept called links between processes. You link two processes together. It's got nothing to do with communication, you're just linking two processes together. And when a process terminates, it sends an exit signal to the other process, the other end of the link. That's it. And if a process crashes, it will send a signal along the link, and the process at the other end will crash as well. So if I have a set of linked processes working together, cooperating, one of them crashes, they'll all crash. And the basic rationale behind that is if they're all working together, and if one crashes, you probably can't continue anyway, so take them all down. Someone else will restart it, yes?
Is there anything in the link or in the, I'm not sure where in the application model that you specify, I guess like hierarchy of processes where you can say these are critical and these are not, so you can
The supervision trees are more for doing that. I think I've got to say that later anyway. Yeah, but that's a mechanism. Working together, and when processes die, next is process. Great. Yes. So if A link, then B is linked to A. Monitor a process. Right. Another process, I'm trapping exits, it crashes, which I can just receive as a normal message. So I can monitor other process receive loop. That's how it's done. Send me an exit signal, and then I can start cleaning up after them, whatever that might incur. Yes.
So, question: if your process that's trapping the exits dies, it will crash the other one?
Yeah,
right?
most generally.
So you don't necessarily have to send them an exit.
No.
Saying, hey, I'm dying, it'll just die.
Yeah. The very fact that you're linked and the process crashing sends the signal. The crashing process doesn't have to do anything, right? That's inherent in the fact you've got the link set up between them. And okay, so that's the basic mechanism. And that is the basic mechanism. So how do you do this? How do I build a robust system with this? It's great, sounds fantastic, but how do I do it? There are two things, at least two things you need to do if you're going to build a robust system. One is you will have necessary functionality that always has to exist. I'm providing some services needed there. That always has to be there. So if it dies, it has to be restarted because that service always has to be available. It can be a database interface, it can be hardware interface, it can be something, it doesn't really matter what it is, There's some form of service. And the other thing I need to do is, if something goes down, I have to clean up after it. You have to find out all the resources it might have allocated and free them and clean up on what's going on afterwards. Because now it will never free them explicitly as dead. Right? So these are two things, at least two things I need to have to do in my system to make a robust system for it. And the first one we do through something called supervision trees. So we split processes into two types. We have supervisor processes and we have worker processes. And what a supervisor does, it monitors its children. So this supervisor here monitors its children, which in this case is 3 worker processes, and it knows what to do when one of these dies. Its job is to handle these processes dying. So if this process dies, more likely to start them all. So it has its rules how it's going to handle its children if its children dies, and always make sure that it knows what to do when one of these dies. The supervisor might give up. I can't keep going and die myself and pass the buck up to the next supervisor who knows what to do. Yeah, we kill our children in OTP. Probably have to edit this out of the movie, right? We use kill our children, we kill our parents. Yes. Yeah. We never got to make a t-shirt with that on it. So yes. So yes, I'm talking Erlang processes. Okay. So yes, we're not talking other things. Yeah.
It's not just a kill, it's a brutal.
There's a brutal kill as well too. Yeah. That's when the supervisor doesn't give the children a chance to do anything, just kills them straight off, right? These supervisors, there's something called OTP, I mentioned a bit before. They have a set of rules for how they're going to handle their children, for example. So if they want to terminate one of their children, they'll send a signal to it to terminate the children, and it might give them time to clean up and terminate after the process. Doing a brutal kill just kills them immediately. We can't wait. Yes?
Now, are supervisors only supervisors because they are using the tracking exits and not exiting when their children exit, or are they something that's special, separate from just another process?
Okay. So they're normal, in one sense they're normal processes, but the code they're running is just supervisor code. That's all they do, is they monitor their children. You cannot get a supervisor to do work. Right?
So a worker could trap exits and supervise something else, but he's really not a supervisor.
Yeah. So yeah, this, for example, this worker here, it might be a server. And these children might have allocated resources in this server. So when this one dies, okay, this supervisor restarts it. But this server has to clean up after it. And for that, it would use a link. So this server would itself be trapping exits, but it's not a supervisor, and would detect that this worker has died and can now clean up after that worker. Reset things, whatever it might be. That's its job, to clean up after it. It's the supervisor's job to restart it. So we're separating these two functionalities for doing this. So the supervisor keeps things alive, and using links crosswise is cleaning up after the process. Yes? By the language. And I can just, this pattern we arrived at very early on. This pattern of having was formalized and applied to make it that. Yes.
So if you killed the most superior recover from that, or is that
That's a choice to make. I mean, well, yeah, that's everything. And depending, the more critical die, the less you have to worry about it. So you do have some, you do have a sort of kernel that has to work. Right? You can't get around that. Yes.
When the process dies, you get data about what caused it to die. The supervisor can then pour it on the report, or
Yeah, you get a reason for it dying. You don't get the process data, unfortunately. So when a process dies, everything about it goes away. All its data dies or goes away. Any messages in the message queue just go away. The process just completely vanishes. But you get a reason. You can see the reason why it died, right? I did an error. I added two things that weren't numbers together or something like this. I can get that reason. I can also get information about where in the code this error occurred. Was there? Yeah.
So if that process had allocated resources that we now have to clean up,
Yeah.
after, if you don't have any of that data, how do you find those resources?
Okay. When it allocates resources, it will go through another process that does the resource allocation for it. So if I've got some form of shared resource, I will have a process sitting in front of that which I communicate with. That will then, yeah, that will clean up after it. I might actually go directly out. For example, if we've got a TCP connection, okay, I'm talking a TCP connection with the outside world. That will go through a port into the outside world. And if I die, the port will detect that and close the connection. If the connection closes, I will detect that and I can do the same thing after. So logically, it's a process doing that thing through. So it's very consistent with that. Yeah. So yeah, monitor processes, clean up after they crash, monitor co-workers and groups of co-workers dying together. The logic is if you've got a number of processes working together, one crashes and one will crash. Then you can do that, but then you have to do it just.
Is there a facility, or would it be easy to add one? Do something like Netflix is sending an army, or just
Dead simple. There is a built-in function called processes. Okay, so every process has something called a process identifier, a PID. Just a data type which identifies. Built-in function called process, which has a list in the system, and I can just kill signals to them. I can just kill them off as I want. I've done that. So yeah. I have to trust it. Once code's running on my Erlang system, it can do anything. It can start killing off any process it likes. It can do whatever it wants to do. I can't stop it. There's no security in the system once you're in. Right? It's like, yeah.
Well, I'm curious if you can even say, has Ericsson ever run up against problems based on that?
No. It runs everything. It either runs things in boxes. I mean, Ericsson sells boxes, okay. There might be big boxes, there might be small boxes, but there's a box that's hardware and software running in through it, and you just don't let people get into your software in that sense. Yeah, you're talking lots of hardware, lots of interfaces with data coming in, but they're not coming into the programming level.
Buffer overflows, no opportunities
No.
to
No.
get malicious code into
No.
the system.
No, you don't do that.
You have to make sure that you aren't compiling new modules on the fly.
Yeah, the system allows you to do that.
Yeah, it's like if you're reactive, if you write a macro function, push button, you can do whatever you want with that, so it's not safe.
No. So yeah, it's not safe, it's not secure. That was never a goal.
There are things like Lua modules or like
You must tell me more about that. Yeah, Alex. My hobby is implementing languages on top of Erlang. Okay, and I've implemented Lua, so I'm very interested to see what that does. Okay, yeah. Okay, this is the basic mechanism. So it's not secure. It's like letting someone into your Unix system with root privileges, right? They can do anything. You just don't let other things come into your system. Actually, this thing about running the compiler while the system was running, that was one of the things an idea we were toying with. So very early on, maybe not in the practical sense, but in the sense that nothing able to block the system. Running something like a compiler in the system, it should not block running the telecoms application. In computations, it would be scheduled out regularly. Your one towards the end of the day, they would just send messages. Things the Erlang shell, while that was just running percent code at the same time, because nothing is allowed to block the system. Yes.
On the supervisor trees, do they supervisors on other machines, other racks? I mean,
You can, but you generally don't do it. Typically, if you're running, okay, this varies, but if you're running something that's distributed, you will run local copies on every node that's running it, and they will then communicate with each other, rather than at a lower level. You can supervise things on other nodes, but that gets getting more difficult. Then you run into a problem with network splits and things like this, for a network going down, coming up, or whatever it might be. Ah, sorry. Yeah, okay. Do you supervise other supervisors or other processes on other nodes? And generally you don't. You can, but generally you don't do it. You can of course run distributed. There's distributed mechanisms, but typically you will run, if you're running a distributed thing, the service and application, you'll run a local copy on each one of them, and they will be talking with each other. So you will typically tend to talk to your local version of it, which will then do the stuff across them. Yeah.
Is this a good time to ask about scalable distributed Erlang? SD Erlang? I don't know. I've only heard of it. It sounds really cool from the name.
Okay. Yeah. There are a couple of problems with Erlang distribution. I think this is what the SD Erlang is attacking. So Erlang can run distributed. I can run multiple nodes on one machine or on multiple machines, and I can set them up so they all communicate with each other. That's quite easy to do. The basic primitives are built into the machine. And when I'm doing that, I can, for example, just send to a process, irrespective of whether it's here or there, wherever it might be. There is a problem with the scalability of that, in that if you're running, well, it depends who you ask. If you're running somewhere up, say, 50 to 100 nodes, the scalability breaks down because you have full connectivity between all the nodes. And all the nodes are sitting chatting to each other all the time, making sure they're alive and so on. And just, we weren't thinking that many machines originally, that many nodes. I mean, whether it's 50 or 100 nodes or even 200 nodes, that depends who you ask and what they're doing. I don't know how Basho do it. Distributed Erlang. There are limits for it. I don't know which limit. Yeah. And that because there's something called the global name server. And it's global. And it comes and that breaks down the network. So the SD Erlang, I think that's one you're referencing, is, okay, how can I get around this? How can I have 1,000 nodes or 10,000 nodes in a system? So how am I going to work that? Right? I can't do it today. So I think this is one solution is I make groups of nodes. So full connectivity within the group of nodes, but not full connectivity outside the group. That's one way of doing it. We're taking part in an EU project working with that. Yeah. Yeah, there are different ways of doing it, but it's a problem that's there. It's in the software level. It's not in the machine level as such. So you can get around it. But that's a problem. I think what you're referring to as SD-Erlang is a way of attacking this. Because, I mean, okay, it won't be long in the future before 1,000 nodes working together is realistic. Right? So you want to do this problem for it. Yeah, we didn't manage to solve every problem, okay? And we hadn't thought of it. It's quite funny, I can say it now, that we weren't thinking about parallelism originally. We were thinking about concurrency. Our application was concurrent. You have these processes running, they're modeling our problem as communicating processes was a very good idea. It was very suitable for doing that. So we're looking at the concurrency. We're actually running on one machine. Yeah, so I've got some more about that later on. But the Erlang concurrency model scales. Right? So yeah, that's monitor processes. Code handling, we do code handling, yes. Well, everything's compiled, all code's in a module. The module's the unit of code handling. You can't compile one function, you compile a module. You can load modules in, you can delete modules. You can have two versions of the same module in the system at the same time. And this very the code, right? Get. And when I load the system, I know exactly what's going to happen when I load a module into the system. And that to do code loading properly. This is of other systems allow you to do that. I mean, Lisp systems have been allowed you to redefine. But what if I redefine? I'm in the middle of evaluating. Going to happen? I don't know what's going to happen in Lisp system if you do that. I know exactly what's going to happen in an Erlang system if I. Yeah.
This has been incredibly helpful.
Yeah.
Patching things with a database.
Yes.
This is really, really handy.
Yeah.
Send somebody a patch as a module. They load this in, and you'll get the
It would. Yeah. Yeah.
It just operates so incredible.
Yeah.
Especially after spending all this time writing classic.
Yeah. Yeah. The problem. Well, the reason is you need to know exactly what happens. When you do that, then you can handle code loading. Otherwise, dynamic code loading. Otherwise, it's very difficult to do it. Otherwise, not certain what's going to happen. And that, I think, that's one, for example, the dynamic code loading, that was also in from very early. That's one reason why you don't have a static type checker. If I static type check the whole system, what happens if I load in a new version of a module with other types? How do I do that? Now, I'm guessing someone else can do it. I wouldn't surprise me if there's someone in Haskell who's done something like this that works, right? Okay, they do some quite fantastic things with type systems. But that was one of the problems we're attacking. What happens if I just load in a new version of the code while the system's running and the functions are different? I might have other functions, new functions. I might have changed something in the functions so they're not type compatible anymore. Or I might be loading in a couple of modules that are different from this point of view. So how do I do that? So our solution was, don't do static type checking, do runtime type checking, and all checking is done at runtime. So when I call a function in another module, we detect if that function exists when we call it, not earlier. So everything's done at runtime. That's also one reason. See, you've got all these things, handling errors. Well, it's not that critical if you pass type check type errors into the runtime system because it'll handle it anyway. I know this is very, very bad. You want to keep errors down, but it works. Not to. Be completely wild about retyping things when you're dynamically reloading modules, of course, but it allows you to do it. Yeah. That is, it's a set of patterns. How do you build fault tolerance of that? and a generalization of it. It's got absolutely nothing to do with telecoms. The name was politically correct in a telecoms company, right? So open's always good. Open's fantastic. It doesn't mean anything, but it's always good, right? Everything's open, so fantastic. We've got nothing to do with telecoms. If you want to rationalize, you can say, yes, it's for building telecoms type applications, but I don't know. And well, it's a platform, I suppose that's okay. So this is a set of design patterns and support code behavior for doing that. So for example, if you want to build supervision trees, you have a supervisor behavior in which implements a supervisor design pattern, which you then use to build your supervisors on top of it. If you want a client server, you use the gen server behavior, which implements that, and it works together with a supervisor, so the supervisor can supervise trees for client servers. They work together. You have other worker processes as well for doing this. Okay, you've got all the standard libraries, but this is more specific. You have a set of support functions if I want to write my own behaviors. I find none of the existing supported provided behaviors fit exactly what I want to do. I'll write my own. I have all the support I need to do this and plug it into the system so that it all works together with everything else. Right? Plus, I get all the support from the system. I get a lot of architecture support. I get logging support if I want to. So I turn on the SASL support, system architecture support libraries. I turn that on, and suddenly I get an awful lot of logging as soon as anything happens. Every time a supervisor starts something, it'll send a log message telling me what it started. Every time a process crashes, I'll get 2 messages from the process telling me it's crashed, and 1 from the supervisor telling me the child's crashed, etc. All this just built into the system. It's very nice. So yeah, if you're building serious Erlang systems, you will use OTP. You mightn't use OTP behaviors for everything, but at least you'll know why you're not using them. And again, it's not. They're actually, yes.
Is there a way for this no crashing?
Yeah. Okay. 2 ways of doing it. One is when you start a process, you tell the process, call this function. And that got the reason normal. And I can also explicitly the reason normal. That's not a crash. And most don't crash. So you don't want processes to crash, but you want a system that can handle processes when they do crash. That happens. Yeah. So OTP, you will always use it. You will at least start using it. You have to find a reason not to do it. Just a point here: systems with Erlang, built with Erlang, tend to be very OS-like in their handling of processes. So you generally set up a large number of processes in the system which provide services, which you then use. Other things can do with it. And you very seldom have a central thread of execution. At most, this central thread of execution will start other things. Right? So it's very operating system-like. In an operating system, you start up a lot of processes doing things, then something comes in, you start a new operating system process for doing that thing, which will then use the other ones. When it's done, the process will end. Like starting a shell, for example. You start a process running a shell. When the shell is done, the process dies. It's the same thing in Erlang. You start your system, which create a lot of processes providing services, and then when something happens, you'll run a process for doing that. Like, for example, using Cowboy to write a web server. Every time new connections come up, that will start a process for you which handles that connection. You will very seldom from that process start up other parallel things. It'll be running in parallel with everything else in the system. Then when the connection goes down, the process dies. And every time you get a connection, you get a new process running. So it's seldom in that, okay, services might start processes for you, but seldom in the application itself I will start a parallel process doing something while I'm running my thing. It also means that this process that's doing the action, that will be most often written in sequential style. It will want to first do this, then do that, then do that, then do that, then I'm done, I die. And I can write that process. I don't have to worry about blocking anything else, because I'll never block anything else anyway. I don't have to sit and think about 5 seconds and not block anything. I don't have to sit and that was non-blocking part of it. I don't have to do that for the system. And it will do enough essentially. And I don't have to program these in a non-blocking style, because I can just go out and sit and wait. This is how I program a processes and operating system. I just run them through sequentially. I don't have to worry about blocking other processes, because the system will take care of it for me. It's the same thing here. Yeah, okay. 2 more things left. We're almost done. Sorry. Kick out. So if we go back to this list of things here, the list of our description of our original problem domain, if you start looking at that, you will find most of that is not telecom specific. Most of that's quite general. I do want to be able to handle a large number of concurrent activities, irrespective of whether it's a telephone switch or whatever it might be. I want fault tolerance and errors. My system should not go down. This has got nothing to do with telecoms. I want to do maintenance. I want to have continuous operations. My system is large. Okay, I mightn't be controlling hardware. I might be talking with sockets, but same thing here. I want distribution. If I want a truly fault tolerant system, I need to run a multiprocessor system. I do have this requirement of actions. As I said, a lot of things are hidden in there. I do want my system to be non-blocking. I do want low latency times, which means that nothing is allowed to block the system. So there are about 3 or 4 points that are sort of hidden in the top one, that are critical to the data systems. So this is not just telecoms. And that's why Erlang has been successful now, right? Because it's providing these things which aren't telecom specific. And I will freely admit, we didn't plan this from the beginning. This is something that came up later. We were trying to solve our problem. And the Erlang concurrency model scales, right? It just does this. Having multiple processes, having communication by sending messages between processes, having no shared state, no global state scales. As soon as you start sharing things, but that hits you really after a while. And it's very difficult to make it. So just as an example, it should be transparent to the programmer. I should, when I'm designing my system, cause whatever it might be, I should worry about that when I'm designing my application. Sometimes you might want to, but most of the times you don't. Right? It's schedules. Okay. A number of schedules in the system. So this is one operating system. The whole thing is one operating system process, and each scheduler is a thread inside there. This is not something I start by my hand. I start the Erlang system and it starts them for me. Now each scheduler is an autonomous Erlang machine. So it's got its own memory management, it's got its own run queue, it's handling and message passing, and it does as much as possible alone. Of course, they're all running one Erlang system, so it's not alone. does as much as possible. And by default, one of these threads is started per core. So if you start up Erlang on an 8-core machine, you'll find 8 schedulers running on the cores. I can control that. I can say, yes, I might have 16 cores, but I only want to run Erlang on 12 because I've got something else I want to do with the other 4. I can control that. By default it does. Each one's got its own run queue. They all try to run as separately as possible. As much as they can do themselves, they do it themselves. Of course they can't. I mean, they're all cooperating within the same Erlang system, so they have to cooperate. They try and do this much as self. So you want to avoid locking in synchronization because that's very costly. So yes. So one of the things they do, for example, is load balancing. So if we've got these schedules running on the cores, we want to balance these as much as possible so they're each running as similar to load as possible on the system for it. I don't want to have to sit and push my processes out. I want the system to do that for me, right? And it does. It puts quite a lot of work into the balancing for it. And it works in 2 ways, which is quite fun. It both tries to spread the load as much as possible, make it as even as possible. If you've got time after, I've got an example of that. The spaceships. And at the same time, it detects, yeah, I don't need all these cores. I might have 8 cores, but I actually don't need more than 4, so I'll try and shut them down at the same time. Reduce energy consumption. So it's both time, compact them and spread them out at the same time, so it's quite fun to watch it. But so we'll go process on the schedule. So we'll go and look at it, or has before got anything as run queue I can take. And I will now. If S couldn't, it will then go until. So all the schedulers are doing this when they've got nothing to do with the. So, and they only steal from run queues, of course. Nothing ever that's either running or suspended. That's one functionality. The other one is a more global. This is the other one. Stealing is purely local. The other ones are more global. So I've got all these schedulers running, and the first that hits, I think, is 40k reductions, 40k process function calls. Decides, yeah, I'm a master now. It doesn't stop or anything. It just goes out and starts talking to the other schedulers and working out how much work have you been doing since the last time someone was a master. And from that, it can try and work out, yeah, I can spread, if I tries to work out at a more global level how I can spread things out to try and balance the load better. And we'll do that. It doesn't stop while it's doing it. The system's still running. We're not stopping anything. That would be critical. Yes?
So I guess, well, the question I have, so the longer the beam's running, the more efficient it becomes?
Well, it spreads things pretty quickly. It does that pretty quickly from the beginning. But it's adaptive. So if you start killing processes, you will find you might be killing them on one scheduler. It'll be moving things over to compensate for that, to keep the load as even as possible. So it's both doing it at a local level and a global level. And then when it's done its work, it just says, no, I'm no longer the master, and everything keeps on running until the next scheduler comes up and hits the limit, and it takes over and now becomes the master and does the bit of global stuff again and keeps on going. And it just schedules these things. It puts this information to the other schedules run queue saying, take this process and this type of thing for it. So we're not stopping anywhere. That would be critical. That would be totally illegal to stop things for it. So yeah, we have these, and at the same time we've got the compaction at this level saying, yeah, we've got more work, we've got more cores than we actually need, maybe we could try and compact them. Basho ran into that problem. Yes.
Is there anything that's chosen taking into account how busy the potential master is?
It probably, I can consultants, Erlang Solutions consultants work with the OTP team, and he's actually in the group with the low level. So yes, yeah. This is not trivial. Anything else? Okay. They're not doing it the easy way. They're just so it doesn't cost you anything in execution time to have a lot of processes just sitting around waiting for messages. That's typically what your system will look like, to be honest. They become runnable when it comes on. And a running process, that will run, it will either suspend waiting for a message, or after 2,000 reductions, it will be rescheduled. And again, this is to make sure that no process ever blocks the system, even blocks the schedule. So you have this preemptive scheduling built into the system for it. And that's why, for example, when we're running this today, while we're actually running 100% load on the system, on all cores on the system, we can actually go into the shell and do work because the shell is just a process and that wasn't being blocked. So that works, right? I think it was the I/O that was causing the load.
We have 10,041 processes running.
Yeah, and they were just, one process was just sending out messages to everyone else in a completely uncontrolled fashion. And the message queues were building up, but it didn't crash. Okay, yeah, ports are all scheduled as well. They're managed by the schedule as well, and they run on the same scheduler that the process that opened the port ran to it. And they're not preemptive. Typically, this is no problem because you're talking to something with the outside world anyway, so that's okay. But there is something called a linked-in driver which allows you to run C code directly on the same machine in the port. So from the Erlang point of view, it looks like it's sending messages backwards and forwards, but you're running local C code. And there are tricks to make that non-preemptive. So yeah, a little bit about process memory, and I think we're done after that. Unless you have more questions. So process memory here. Each process has its own heap. And all process data is local to a process. So we're not sharing data. Well, in one way we're sharing data, but that's very limited. We're not sharing data between the processes. So each process has its own heap. Nice. That means we were paranoid about safety. Okay, things should not crash the system. But that about it. This is not required by but data in the process. There are a couple of reasons for not doing this. It's not just by chance. Copying data, isn't it? And the answer is yes, well, perhaps, sort of, maybe. But there's a very big but at the bottom, okay? It has a lot of benefits doing it this way. And they're actually getting more and more. So, for example, having separate heaps has benefits. It allows me to garbage collect each process heap separately, which means I will never have long garbage collection times, which means I won't interrupt the system while doing garbage collection. Most process heaps are tiny. Garbage collection times are negligible. I won't notice them in everything else. That's a really big win. I don't have to have a full real-time garbage collector that works on multi-threads, which is difficult, to say the least, right? I mean, the only one that works in the JVM is one you have to buy, what is Hazel. They have a system that does that. And that's definitely not a trivial problem to do. We can avoid that. It also means we lessen synchronization. My process heap is being run by one thread. It's only that thread, it's only that scheduler which accesses that heap. I have much less worry about synchronization between other threads. And synchronization is very costly. Garbage collection, and by the way, the synchronization problem gets worse the more cores you have. The more parallelism you have, the more it grows. garbage collection becomes much more efficient. I can basically get into low level here, I can basically do a stop and copy collector for one process, and that is much more efficient than doing a real-time collector. So I've done a couple. And yes, I've written not on a single core system, I've done a number of Erlang implementations with shared heap. And yes, I could send very large messages around process rings extremely fast, but when it got down to actually running a real code, it was about the same time as copy, because the collector is less efficient. And this isn't a bad implementation. You're just doing less efficient. It becomes when you got health and you have an absolute you just see it's wrong. You have a okay. The Erlang machine is quite common. There are types of memory, different of so not garbage collecting its memory separately as well too. There's a lot of work into doing into this. And you avoid problems like cache coherency. It's great having one copy, but if that's cache, the cache coherency problems of multi-core is quite difficult to get that to work. And you can get very weird states, someone told me, that it costs more to read from the cache than to write to the cache because of the coherency problems you've got. So having separate copies might actually be more efficient and cache-wise doing that. And, yeah. Okay. Yeah, they've either got rid of the locks or made them very short. I think they got down to message passing and sending to 2 writes into the other process for it. I think they can either do that without locking if they're careful. So you're building on the sending heap, then you're pushing pointers over to the other side from that memory area into the other process. It's definitely not trivial for it. And a lot of the complexity of the Erlang, of the beam, comes from making it run on multi-core systems. Running on a single core, it's comparatively simple. Running on multi-core suddenly becomes very difficult if you want to make it optimal, which we want to do here. Yeah. And almost done now. So the garbage collection process, it's a generational garbage collection scheme, which is a very nice heuristic. The basic idea is that most data you will die old. You will be able to reclaim it very quickly. Very little data will actually be live for a long time. And this is a very good heuristic for having immutable data because I'm always creating new data all the time. And this means that when I do a garbage collection, I can just collect the new stuff and I'll reclaim most of the have to do it, but that's much less. I can control as well. So this is nothing. It just do it one copy in each. Yeah. So just wind up here is everything. They're definitely. At least write the number in Erlang. It will do it, but it's slow. So as I say, tomorrow. Things and controlling other things to do it. So, like the Ericsson products that use Erlang, the signal processing, the data processing may be running in DSPs or FPGAs at the low level, but they'll be using Erlang to control them and to manage them and set them up. And for that, it's perfect, right? So yeah, so be very aware of that. And most Erlang applications work together with things written in other languages, if you start looking at them. Even our original systems did. We were talking with switches, which was hardware with other software running on it, literally assembler in those days. So even from the beginning we were doing that. And I just want to wind up with a pat on the back and telling you how good we are. Okay, right? So this is a list of some of the systems I know running Erlang, and it's not complete. I know that. Some companies just don't say anything. Some might be secretive, and some just don't bother saying anything like this. These are people I know running Erlang. So, well, Basho running React, of course. Other things, Ericsson, yes. We're up here somewhere. WhatsApp, of course. I'm very interested to see what happens with them now that Facebook's taken over and how they're going to implement their system. Bet365, that's a British international online betting company. They run part of their system in Erlang. So if you go onto their site and watch the football matches, you can actually bet on the football matches while the match is going, and the odds are changing all the time, and using Erlang system to send out the new odds. Yes?
Is the Battlestar Galactica really run on Erlang?
Yes.
The Cylon.
The game. The game, okay. But you can use it in the spacecraft as well too, yes. Yeah. So Basho, Wooga is a German, I think it's some of their games are written in Erlang, and they found it increased their load capacity by about a factor 10 on some comparisons we're making for it. A lot of places use it in many things. Yeah. There are a number of tools that are based on Erlang. I saw that on one table. They had some. I don't think it's in space, although someone has told me that it is in space. I don't know if any. Thank you. I'm on Twitter as well if you want to tweet me. Yes?
I was struck that the message passing model just reminded me very much of Tony Gore's communicating sequential processes. Was that just a fortuitous happenstance, or did that influence what you were thinking in terms of message?
We knew about it. I don't know how much it influenced it, but we did know about it. That's where the bang comes from, amongst other things. Originally, when you sent a message, you got the sender for free. That doesn't happen now. And there you would have a pattern with the question mark in with the message and the sender for it as well too, which I think also came from there. So we definitely knew about it, yes. We didn't, okay, I'm not going to say now, we didn't invent a lot of this stuff. A lot of these things we weren't first for. So for example, in Ericsson, there were other languages having processes and communication. There's a language called Pascal, which was built on top of Pascal that did this, which were doing that as well too. I don't know what happened with that language, so we didn't steal that. Of course, we weren't the first to implement processes. We were doing reactive programming, which is big today. We didn't call it that, but we were doing it, and we definitely weren't the first doing that. Maybe in the functional, I don't know. But the logic languages were doing that a long time before. Yeah.
So a lot of these ideas have crossed over into other languages and
Yeah.
other actor systems, and reactive is taken on.
Yeah.
Are there parts of Erlang that you say, I mean, there are gems that you know that haven't crossed over that you think, man, I wish this would really catch on in other places?
I don't know. I mean, if you look at akka, for example, it's got message passing, it's got error handling and things like this for it. But though someone has to correct me here, it does it at the it does it at a higher level, rather the OTP level than at the low level. I would say what other languages haven't got is this collection of them. It's not just processes and asynchronous message and so on. It's the lightweight process. work together with process isolation. So it's all these things for it. That's why it works, right? Because not just because you got one of them, but it has go channels, but it doesn't have the preemptive scheduler. It, yeah. But you've got shared data.
And if you call a function, it's preemptive.
Yeah. But if you go into a loop, it isn't.
Yeah, there are a few.
Yeah, yeah.
locations.
But you've got shared data. You've got shared data. If I remember correctly, the model is you're sending messages to do the synchronization, and you're passing data by sharing data. That's inherently unsafe, right? That's not a problem with Go. Just the very fact that multiple things can rewrite in the same data area means that it's unsafe for it. So I'd say from the Erlang point of view, it's this collection of everything that fits together. That does it more than anything else. And other languages have taken ideas. I'm not saying Go is taken from us. I know Akka and Scala have. Akka has, but Go's done its own. Go, for example, doesn't have process identifiers for that concept. Yeah, they just. It's got its view. Okay.
Its own ancestors.
Yeah, yeah. I mean, every language, every system has a view of the world, right? How do I want to model the world? If you're coming, say, from Java, you've got an object-oriented view of the world. You model the world as classes and objects and things like that inside it. From the Erlang point of view, you model the world as processes, communicating processes. So when you're building Erlang systems, what you tend to sit down and do is say, yeah, what concurrent activities have I got on in my system? How am I going to put processes in, what they're communicating with and everything like this. Then you maybe put the error system on top of that and things like this for it. Then that's how you model it. Yeah.
One thing that's always kind of struck me about Erlang since I first heard about it probably 15 years ago. In the early and mid 80s, Marvin Minsky was working on a society of mind theory. Danny Hellis formed Thinking Machines Incorporated, massively parallel supercomputers.
Yeah.
And I know Erlang Solutions is working now with the Parallel board.
Yeah.
I'm curious, where's that at now? I think it's going.
Okay. I don't know how many cores the beam can handle in one go, but the other ones I don't know. I think that concurrent parallelism. We didn't have parallelism before, and it just worked on parallelism. About you have cores in one Erlang node. I mean, it'll break down after its level. Then it might be better to have lots of nodes, them communicating with each other, each one working with it. Then you need to be able to handle lots of nodes. So you need to work that problem, solve that problem as well too. They're definitely making it, scaling it more and more when they're working on it. So I mean, the multi-core Erlang, I think it could handle 4 cores before it sort of leveled out or something like this. Then later it became 16. I don't know what's up to now.
The original connection machine, the CM1,
Yeah.
had 65,000 processors in it. When I was reading about Erlang's processes in the mailbox, it struck me the similarity between that and how the connection machine was designed.
Yeah, okay, yes. You could definitely do another implementation that worked at that level. And no one's done one, as far as I know. No one said anything about it. I think as yet, it's not interesting. Not interesting in the commercial sense.
I don't think anybody has figured out how to write applications
it's bad enough in many applications you get up to 4 or 8 cores and using them sensibly. I mean, there's an awful lot of applications that are still single-threaded, right? For it.
Well, and you run into a data locality problem before you run into a computation.
Yes, yes.
So you have thousands of cores, but actually accessing data that's relevant to each one is.
Yeah, you will end up with NUMA type architectures. Then it might be better to run one Erlang node in one block of cores that fits together memory-wise and have separate Erlang for that. Yes, I've got more costly communication between the Erlangs, but each one will run much more efficiently on its memory. So going, yeah, that's another problem. That's another. It's a process or a few processes, but running multi. Okay, yes, we have systems running thousands of processes, but how you scale that, I don't know. In each process.
Just a comment. You see the same thing on the data center side. People using so it's kind of both.
Well, I mean, as everyone knows, the war, right? We have to rethink. Just nothing around that. And I came from the gaming world, and in doing that, they had this running through all the objects in this thing in one central processor loop, and for them a comparatively long time before they could actually use multi-cores, which is very strange. Yes, you had a question.
So when you were informing you had implemented an actor system, and you like went back and researched that, was there any did you end up incorporating some of that research into future versions of Erlang, or did you?
We'd basically done it by that time.
Okay. Was there any anything that they had pointed out that you wish you had known about earlier, or?
Not really, no. As I said, we were solving the we were solving the problem, right? That was our goal, to make the best solution we could come up with this problem, rather than implement something specific. And we found that our solution was good for what we were trying to do.
You feel like it was a really large problem?
Yeah, in retrospect, it was. We didn't realize it in the beginning, to be honest. We didn't realize how general this was. Not until later on in the late 90s it was. So I was a member of a group that left the Erlang Computer Science Lab and formed a company called Bluetail, which was one of the first companies outside Ericsson to use Erlang in products. And there we were using the parallelism in the system. We were building sort of front ends interfaces into back-end servers, and trying to bring sort of telecoms type reliability into the web in those days, which was pretty bad, right? And there we're using the concurrency. Yes, we're using this. Every connection gets a process. We're using the distribution mechanism to handle failovers and things like this for it. And yes, that's when we sort of got out of the telecoms world and using the Erlang features to do this. But it took a while. We definitely didn't think about this from the very beginning. We weren't looking at that. Which was also quite fun to program. Else as well too. Okay, other people have thought about it. I'm talking about myself now, so I'm not going to say that.
More about worker on node A, and I wanted to worker on node B. What's the best way to do that? Would it be a remote procedural call? Would it be just contact B's supervisor and he'll start a new one?
They contacts the other processor's supervisor.
Okay, like via remote procedural call? Or?
Via remote procedure call or something like that, yes. Okay, the reason for that, one reason for that is if you're running a supervisor, the supervisor has to start the process. You can't hand over a process to a supervisor. You have to tell the supervisor, start this process. That's just the way the supervisors implement it. So yeah, in that case, I would do an RPC to it and say, start this child for me. And I'll get back the bit for it. So yeah, this works. And you had it. Questions?
No, I just had filler. Are you still working on LFE?
Yes. Yes. LFE, yes. Okay, thank you very much. LFE, that's for those of us who like parentheses. It stands for Lisp Flavored Erlang. It's a Lisp implementation running on top of the Erlang machine, accessing all the Erlang libraries. So if you want to write things with parentheses, you've got LFE. You've got full power of Erlang, all the systems in Erlang, all the libraries, all the properties of the machine, everything. Plus you've got parentheses, you've got macros, you've got all the Lisp goodies as well. Yes, it's still. Well, it's Lisp. Okay, it's not Common Lisp, right? It's not Common Lisp, it's not Scheme, it's a Lisp that's designed to fit on the Erlang machine. So for example, one thing that's a bit difficult to do on the Erlang machine is mutable data, which rules out a lot of standard Common Lisp programming. So yeah. So if you want to use Lisp, it's there, fine, it's supported, I'm running it, it actually works. No known bugs. Okay. A couple actually. There's interest there for it. I've got a prologue. Pardon? Yeah, I did a 0.9 a couple of weeks ago. Better. So now you can start up LFE and run LFE. The app. Yeah. The LF. That's the thing I've done for it. So that's one time around. Put up yet. I've got a prologue system if you're running on Erlang, if anyone's interested. And I've got a Lua as well. And these three have now got users, which makes it slightly more difficult. But they are being supported. Okay, yes. So yes, yeah. Are you interested? It's there. Lua, LFE. Sorry, LFE. Yes. Yeah. Okay. Look at it. Yes. Yeah. But I can say it's not Common Lisp. It's not Scheme. It's a Lisp that's been designed to fit on top of the Erlang machine. Okay. So it's got no mutable data, but it's got pattern matching built into it and things like this for it. And you can access all the sends, receives, everything like that as well. So I think we're getting turned off soon. So yes. Any last question? One more. No. Okay. Yeah. Please mail me questions. I'm also Virding on Gmail if you want to use that instead.